Thank you all for being here. I'm Kartik, and I'm going to tell you about Memo, a new programming language that I've been working on. I wanted to start this talk by playing a game invented by a philosopher named David Lewis. And here's how the game works. You're sitting at a table, and at this table are three objects: a pink circle, a green circle, and a green square. And sitting across from you at this table is your partner or your teammate. It's a collaborative game. You're in it together to win it together. And your partner is randomly assigned one of these three objects to communicate to you. But your partner is only allowed to use one of four words to communicate. Your partner could either say round, green, square, or pink. OK, so suppose your partner says, can you please bring me the square one? Can you all just point for me which object would he pick? Come on, guys. Great, strong preference for the green square. It's the only square one. Suppose your partner says, can you please bring me the pink one? Can you guys please point for me? Which one would you pick? Great, strong preference for the pink circle because it's the only pink one. But now suppose your partner says, can you please bring me the green one? This one's harder because there's two green objects, the green circle and the green square. So what are you supposed to do? Well, perhaps surprisingly, people tend to have a preference here. And the preference is for the green circle over the green square. This is a real phenomenon. It's robust. Here's some data from a replication by Chen and Franca in 2015, where they found that about twice as many people picked the green circle over the green square. So what's going on here? What's breaking the symmetry between the two green objects? Let's try to analyze this game as we would analyze any game. Suppose I am the listener in this game, and suppose I heard the word green. Well, we just established that a priori, it's just ambiguous whether it's the green square or the green circle. But when we play games, we don't just play at the literal level of the rules of the game. We think strategically. We think recursively about how other players in the game might be thinking. So let's think about how my partner, the speaker in this game, might be thinking. Suppose she's trying to communicate the green circle. Well, she could say green, which is ambiguous, or she could say round, which is also ambiguous. So my partner is actually also in a bit of a pickle. But again, suppose my partner is not just thinking literally, she's thinking strategically, recursively about other people in the game. Then an interesting thing happens, because my partner can do the following thing. She can say, Kartik knows that if I were trying to communicate the green square, I wouldn't say green, I would say square, because square is unambiguous. When I said square, you all pointed to the green square. So Kartik should be able to infer or deduce that if I said green, the risky, ambiguous utterance, then I was probably not referring to the green square. I was probably referring to the green circle. Does this reasoning go through for everyone in the room? Can you guys nod for me? Yeah, OK, fantastic. This way of thinking about how words tend to get meanings in everyday pragmatic language use is called the Rational Speech Acts framework. And it's been very, very successful, very influential in cognitive linguistics, in part because if you were to write down a computational model of how you would do this recursive probabilistic reasoning about people thinking about each other under uncertainty, you would find that the output of that model predicts people's behavior really well, just beautifully precisely. If you were to go out and collect data on people's intuitions in this game, it just matches the model really, really well. And it's actually not just linguistics. Across a wide variety of disciplines, people have just found empirically that models of recursive social reasoning under uncertainty predict people's behavior really, really well. Now, in my PhD, I've been lucky to get to work with people across actually all of these disciplines. And when I say work with, what I mean is sit next to and pair program models with. And over the years, I've come to the conclusion that people in many of these disciplines are writing code bases that actually look very, very similar. Their models all kind of share these common themes and common motifs. In fact, I have become persuaded that there's a whole programming paradigm lurking here, a paradigm that I've been calling the recursive rationality paradigm, where by rationality, what I really mean is being Bayesian in the face of uncertainty. And so it's not just a programming paradigm, it's a probabilistic programming paradigm. That's the good news. The bad news is, having spent, again, many years of my PhD sitting down and working with people across all of these disciplines, who, by the way, tend not to be professional programmers, they tend to be scientists by training, I've come to believe that programming in this paradigm is really hard. And I'd like to actually take a second to try to convince you of why programming in this paradigm is hard. I think programming in this paradigm is hard actually for the same reason programming in any paradigm is hard, which is correctness and efficiency. Here's the problem with correctness. The problem with correctness is that when you're thinking about people thinking recursively about other people, you invoke this rich vocabulary of words like believe, think, see, do, know, want, imagine. But when you're writing a probabilistic model or programming in a probabilistic programming language, the words you get to use are words like sample, infer, condition. So as programmers, you're constantly translating between believe, think, see, do, know, want, imagine, and sample, infer, condition. And who knows if the semantics are preserved. And if they're not, you end up with a whole bunch of really tricky, subtle bugs. Bugs like having one agent secretly have mind control over another agent in a way you didn't anticipate. That's the problem with correctness. The problem with efficiency is that when you have agents thinking recursively about each other, there's this combinatorial explosion in possible states of the world you have to keep track of. Not just possibilities of the real world, but imagined possibilities of imagined worlds, imagined by possible agents, imagined by other agents. You can see how this rapidly gets out of hand. And in fact, in practice, if you ask a cognitive scientist, they might tell you that running their model and fitting it to data might take not just minutes or hours, but actually days of compute. And I think that this is a fundamental roadblock to the progress of science in many disciplines. Because if you're a grad student and it takes you 3 days to test your hypothesis because it takes you 3 days to fit your model to data, then you think about science in a completely different way than if it takes you, let's say, 3 hours or 3 minutes or even 3 milliseconds to test your hypothesis. Okay, so over the past couple of years, I've been thinking about how to address these problems. And I've been trying to do that by building a new tool, a new programming language. And that language is called Memo. Memo is a domain-specific probabilistic programming language. And it's specialized for the domain of models of people thinking recursively about each other. And here's what Memo does for you. It addresses the problem with correctness by being designed not around the sampling of random variables like nearly every other probabilistic programming language on the market, but rather around agents who make choices. In Memo, you use words like believe, think, see, do, know, want, imagine, and the semantics of these constructs protect you from the kinds of bugs I was talking about before. As for efficiency, Memo realizes that when you're thinking about possible worlds, almost by the definition of possibility, these possible worlds are independent, and you should be able to compute over them in parallel. And so Memo compiles models to parallel array programs that can run really fast on modern hardware, like on GPUs. In fact, specifically, Memo compiles models to JAX. Okay, let me give you a little demo of how you would use Memo to build the model that I described for you at the beginning of this talk. The first thing to say is that Memo is embedded in Python. And so when you start writing Memo, you can just start writing Python. For example, to set up the rules of the game. In this game, there are 3 objects. Let's call those reference to borrow some jargon from linguistics. There's these 4 words you get to use. Let's call those utterances. And of course, we need to write down which utterances describe which reference. So for example, green describes the green square and the green circle, but not the pink circle. Okay, the next thing we have to do is say, well, what do we want to compute? So I told you that Memo computes arrays. The type of array we're interested in here is just like the data table from Chen and Franca that I showed you earlier. So we want an array that's the data table prediction of if a listener in this game heard some utterance U, then what's the distribution of reference that they're likely to guess? Okay, the next thing to do is to set up the recursive reasoning. Now, when I described this model to you, what did I say? I said there's a listener. The listener thinks there's a speaker. The speaker is given a referent to communicate, and then the speaker chooses an utterance with which to communicate it. Here's how you write that in Memo. You say there's a listener. The listener thinks there's a speaker. The speaker is given a referent, and the speaker chooses an utterance to communicate. You write this model the same way you would explain this model to like a friend at the bar. Okay, how does the speaker choose an utterance? Well, there's 3 factors that are important. The rules of the game, so the utterance must be denotationally consistent with the referent. There's recursion. The speaker thinks recursively about how the listener might be reasoning, and so notice the recursive call to the model L that we are currently building. And finally, rationality. The speaker chooses with a softmax over the probability that the listener guesses the correct referent. And notice, by the way, that these 2 terms introduce these new parameters, the number of levels of recursion and the softmax, or the temperature of the softmax. Okay, we're really close. Only 2 more things need to happen. First, the listener needs to observe what the speaker says. So this is kind of like conditioning. And the listener updates their belief. And finally, the listener makes a guess. They guess which reference the speaker actually meant. And finally, we compute a distribution, or a predicted distribution, over the listener's guesses. And that's it. That's the whole model. If we run this model at t equals 0 with no recursion, here's what it predicts. It generates a data table indexed by utterances and reference. And for example, this data table tells us that if the listener hears the word square, they're 100% likely to pick the green square. This was borne out by the experiment we did at the beginning of the talk. However, this model also predicts that if the listener hears the word green, they should be perfectly 50-50 between the green square and the green circle. And that's not quite right. That's not consistent with Cheng and Franca's data. However, if we run this model with one recursive level of reasoning, so at t equals 1, it does predict a preference for the green circle over the green square. Now, let me compare this model with how you would write it before Memo, so using an ordinary probabilistic programming language. The code on the right is something I took verbatim from a computational linguistics textbook, and it's written in a probabilistic programming language called WebPeople. And let me make a few remarks about this. Firstly, I think that the Memo version matches our intuitive description about how we would talk about this model. It uses words like believe, think, see, do, know, want, imagine. It's about 10 times faster on the same CPU, and if you were to plug in a GPU, it would immediately start using that without needing to change any code. It's end-to-end differentiable, so you can optimize parameters like this at softmax temperature by gradient descent. Because it's all in Python, you can use the broader scientific Python ecosystem, like you can make plots with matplotlib, and because it's fast, you can even make these interactive plots that refresh live and really let you get a sense of how the parameters affect the predictions. And finally, it integrates with the broader JAX deep learning world because it compiles to JAX. We've implemented a lot of models in Memo, and each time we do so, we find that they're several orders of magnitude faster than the best implementations we can find online. And generally, you need to write dramatically less code in Memo than otherwise. Perhaps for this reason, Memo is used by a lot of labs around the world now, and several papers have been published that use Memo models inside them. Memo has also been used as a teaching tool in a lot of courses and textbooks and summer schools around the world. Maybe the thing I'm personally most jazzed about is that the cognitive science and philosophy of mind communities have been using Memo not only as a tool, but also as a way of thinking about what theory of mind even is. And over the past few months, I've written a number of papers that try to argue that ideas and motifs from programming language theory can actually be really useful for us to understand how minds think about other minds. And I'll just make a plug. If you want to hear a little bit more about this, you can come hear my talk at Onward tomorrow at 11, and I'll say a little bit more about that. One more slide. I wanted to end by saying that this paper that I just presented has the longest acknowledgement section that I've ever published in a paper. I'm the one up here giving this talk right now, but this project wouldn't have been possible without the help of actually dozens of people across dozens of fields and disciplines, and I wanted to extend my gratitude to them as well as to you for being here. Thank you.
Okay, any questions? So perhaps I have one question to get started with. So you mentioned that Memo is already being used in many places by a lot of people. What are the comments and what kind of feedback did you get so far?
Yeah, so on the whole, the feedback I get from Memo users is they're delighted that they can write the models in the way that's intuitive to them using the vocabulary that they're trained to use, and they're delighted that it runs a lot faster, and at the same time, they're really excited about learning about array programming and JAX, and this whole world of like high performance computing and differentiable programming and probabilistic programming, like this isn't really very, very common in the community, and I think they just get very excited that these tools exist, and Memo is one thing you can make by putting these things together, but there's so much more, like you can see their eyes light up with like all of the possibilities of things you can do. And so, I don't know, I feel like there's a lot of scope for interesting things that can happen.
Okay, that's great.
Yeah.
One more question?
Yeah, that was a very cool talk. I'm just curious what kind of experiments you've used to model your data using Memo. Do you have any practical examples where you've actually applied it yourself or other labs that you know that have used it?
Yeah. So as I said, a lot of people have written a lot of papers where they run experiments, like actual behavioral experiments. They'll ask real people, with IRB approval, some questions, and then they'll collect that data, and then they'll try to compare that data to outputs of models. I'll give you just one example of this that I personally find very moving. There's a team of psychiatrists at the University of Rochester who are really interested in the dynamics of teenage suicidal ideation. They're interested in how children or teenagers think about themselves and their parents and their therapists kind of recursively in the strategic way. And they just got an IRB and a grant to study this by collecting data in their clinic and comparing it to a Memo model that they wrote. So I find that work really inspiring and exciting.
Cool, thank you.
Okay, thank you again.